Okay, so let's just talk a little bit about what it means to be digital, since we live in a digital age, right? Digital world. First thing we need to know is this idea of binary numbers. Okay, binary numbers. How we do numbers using only two numbers instead of using 10 numbers. All right. We grew up in a decimal world, a base 10 system, and I think the reason this is my own theory, but I think the reason we grew up in a base 10 system is because we got 10 fingers. All right, and that's just kind of how we learned to count. It's actually kind of interesting. The Mayan and the Aztec culture had a base 20, and they counted on their hands and toes. And their numerical system, which was incredibly sophisticated, they actually had much better mathematical system before people did in like Greece and Mesopotamia. They were doing it in Central America, and they were doing it on base 20 instead of base 10. And the theory is it was because they counted on hands and toes instead of just their hands, which is kind of interesting to think about. But we use base 10, unless you're a high-tech, savvy digital person, and then you use base 2. Okay, that's what it means to be digital, is only have two numbers, 0 and 1. Nothing else. Everything is described with two numbers. Okay? That's it. That's what it means to be binary. You don't have the number 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. They don't exist. You've got 0 and you've got 1. Okay?
Base 2 is like base 10. Your fingers are missing.
It's just like if all we did was count on our thumbs, we would be binary folks, but we're not. We're decimal. Okay. Now let's look at a number in base 10 just to get an idea of what we're talking about here. So give me a number in the thousands.
Billion.
1,922. So we write numbers, and you guys have learned this system ever since you were little wee children, and it makes sense to you. But here's what you're really doing. When we write that number, this first place tells me how many 10 to the 0th power I have. I have 2 of them. And 10 to the 0th power is what? 1. So I've got 2 of those. This one tells me how many 10 to the 1st powers I have. I've got 2 of those. So that's 20, right? This one tells me how many 10 to the 3rd power and how many 10 to the 4th power. That's what our placeholders tell us in our numerical system, all right? In a binary system, it's exactly the same, except for it's 2 to the 0th, and 2 to the 1st, and 2 to the 2nd for each placeholder in a binary number, and you only have a 0 or a 1.
Why is it a 10 to the 2nd?
Sorry, I totally skipped that. This is 10 to the 2nd, this is 10 to the 3rd. You're right. Thanks. Keeping me on my toes, okay? But you get the idea of what I'm talking about, right? So since this is 1, I know I have 2 1s. This is 10, I have 2 10s, I have 9 hundreds, and I have 1 thousands. Okay, that's how we write numbers out. And in a binary system, it's exactly the same, except for we use 2 instead of 10. All right? So each placeholder in a binary number tells you how many of that power of 2 that you have. Okay? And they either have a 1 or a 0. Either you have none of those, or you have one of them. That's it. Each placeholder, each little place, each digit in a binary number is called a bit. And generally, we code information in 8 place numbers, which is called a byte. And as you know, if you pay any attention to your phones or your iPods or your computers, we talk about megabytes and gigabytes and even terabytes nowadays. We're getting into there. So we talk about how much information your thing can hold in millions of bytes or billions of bytes or even thousands of billions of bytes. Okay? Okay. If I have a digital number, a binary number like this one, 11010111, okay, I just made that one up. It's awesome. We could figure out what it is. As a matter of fact, why don't we figure out what it is? Okay, remember, this first spot is 2 to the 0th power, right? So that equals 1. And this spot is what? 2 to the 1st, which is 2. And so I've got one of those. So I've got 1 plus 2. And then this is 2 to the 2nd. I don't have any of those, so it doesn't matter. This is 2 to the 3rd. What's 2 to the 3rd?
16.
What's 2 to the 3rd? 8. So I've got an 8. And then I don't have a 2 to the 4th, but I have a 2 to the 5th. 2 to the 5th is 32? Okay. So I have a 32, and I have a 64. So this number I just wrote off the top of my head is 64 plus 32 plus 8 plus 2 plus 1.
Which you wrote as 11.
Which is what? 107? So this number in binary is 107 in decimal. Okay? It does, but it's easier for technology. It's harder for us, but for like a computer, it's easier to keep track of 2 numbers than 10 numbers. Okay? And I'll tell you why in a little bit. But okay? So notice that remember 110. I was like crazy that I made up this weird number that's forwards and backwards. What's that called? That's called a palindrome number right there. Okay. How many decimal places does this number have?
7.
I guess they're not decimal places. How many places does this number have? 7. So what I'm getting at now is that with this many spaces in a binary system, I can potentially write this many different numbers. What's 2 to the 7th? So with 7 places and 2 digits, I could write 100 and whatever you just told me, 128 possible different configurations, 128 numbers with that. Okay? Okay? With a byte, remember a byte has 8 places. Okay? So how many possible numbers can you write with 1 byte? 256? Okay, or 2 to the 8th, whatever 2 to the 8th is. 256? Okay. Okay.
2 to the 8, 56.
There's a term, when we write a number, we talk about the most significant bit. And the most significant bit is the first non-zero one when you start counting, when you start looking at the places from the left. So let me write out a binary number that's a byte. Okay, so I have 0, 0, 0, 1, 1, 0. How many is that? 6, 7, 8. Okay, there's a binary number. It's a byte. It's got 8 places. That's what they call the most significant bit. And the reason they call it that is because that's going to be the largest value that's actually got something. You see what I'm saying? Okay. Because everything comes in bytes. It generally comes in packets of 8. And so the lower numbers are going to have zeros for the first couple decimal places. Okay? Exactly. So the number 1 written as a byte would be 0, 0, 0, 0, 0, 0, 1. All right? The number 2 written as a byte would be 0, 0, 0, 0, 0, 1, 0. That's the number 2. And
you're only writing 7, Mark, but it's supposed to be 8.
Thanks. Okay. Now let's compare analog versus digital. An analog signal, or an analog signal, I was trying to think of another word and it just wasn't coming, okay, is something like this top picture. It's Friday, okay. An analog signal is one that varies continuously. That's always changing depending on whatever it was that was being measured, okay? So it's a continuous signal. It varies between 2 extreme points, but it's constantly fluctuating by whatever's measured that signal, okay? And generally, let's think about music, okay? Because music is one of the things that has been digitized within your lifetime. And back in the early days when I was old or young, and you were, never mind, but you know what I mean? We listened to records. Records were analog, and they were a representation of sound, okay? And in order to take that record and turn it into a sound, your record player would get a signal from the album by using a needle that would vary continuously, just like sound does. When I sing, and it's so beautiful that you start crying, that the sound is constantly fluctuating. A digital signal doesn't do that. A digital signal either is on or off. And that's the only option, because in digital we only have 2 options, 0 or 1, okay? So a digital signal is coded. It's some sort of way of coding this constantly varying signal and coding it in either zeros or ones, either on or off. Nothing in between. You don't have gradual change. You either have on or off, okay? One of the reasons why analog, some people say analog sounds so much better, is because it picks up all the sounds. Whereas digital, what we've done is we've coded to represent all those sounds. Excellent. Okay? Here's what you do. If I want to take an analog signal, something that varies continuously, and this is actually a bad picture of it. If I was going to have a good picture of it, it wouldn't be a nice sine wave like this. It would be more like this. Right? It would vary all over the place because sometimes you're singing high, sometimes low, sometimes there's drums, sometimes there's all sorts of variation. What I would do is I'm going to break it down into lots of small pieces. Okay? And I'm going to look at the average value at that little time frame. This is called sampling. Okay? And the number of times, the rate, what's called the sampling rate, or sometimes it's called the bit rate, is the number of times you sample this signal per second. The higher the sampling rate, the smaller the pieces you break this down into, the better you're going to be. The better you're going to represent that signal digitally. Okay? So what you're going to do is you're going to take the signal, you're going to break it down into small little pieces. It's going to have an average value, and you're going to give that binary number for a value that's within a certain range. And that's how you digitize an analog signal. Okay? So it's called the sampling rate. It's the number of times per second that you measure the signal or you sample it. For a CD, for a music CD, I believe the sampling rate is 44,100 hertz, or 44,100 times every second. That signal, that musical signal, has been broken down into 44,000 pieces and given a digital value. Okay? The higher the sampling frequency, the higher the quality, but the more information it takes. And basically what you're doing, this is what I was trying to explain, is that you break an analog signal down into little binary packets where each number represents a range of values, okay? I'll show you a picture of what this looks like in just a second. The more packets you break it down into, the better the representation is, the less error or the less loss of information, but then it takes more memory to store that data. And the process of doing this is called quantization. You quantize an analog signal by breaking it down into very discrete packets of values. So here's a picture of what I'm trying to explain to you. Okay, look at this upper picture here. So here's an analog signal. The green line is it could be voltage. Okay, we've taken some sort of sound, we've turned it into a voltage that changes, and therefore we can record it and play it back and all that stuff. Now, if I'm going to digitize it, what I'm going to do is I'm going to sample that signal at a certain time interval. So that's what each of these little black dots is. Okay, I've sampled it and I've figured out the value at each of these time intervals. Okay, there and then there and then there, and I've given them a numerical value. And then I give that numerical value, or a certain range, I give that a binary number. Okay, I say the range of 0 to 1 is going to be 1. And then 1 to 2 is going to be 2, and 2 to 3 is going to be 3, and so on and so on and so on. So then I can encode that voltage value as a binary number. The smaller I break these packets down vertically, the better my representation is, but the more information it takes, and the more frequently I sample my signal, the better the representation is, but the more information it takes. Okay? So like here's another one where they've taken, these are the sampling rates, and they've taken an average value and given it some numerical value. All right? Okay. So, what do we do with all this information? Well, basically, we store it, and we use it to do things like to, play music or play games or whatever. And there's a lot of ways to store binary information, because all you have to do is have some way of storing it that can determine either if it's on or off. You just need a 1 or a 0. That's it. You don't need anything else. Okay? CDs are one way of storing information, and
There's no C in disk. It doesn't matter.
yeah, C and K always throws me off from the whole computer thing.
Yeah, C on
Yeah. So here's basically how a CD works. Okay. Okay. So when you want to store binary information, all you need to do is you need to be able to somehow encode whether you want a signal or don't, a 1 or a 0. It needs to be on or off. There's nothing in between. So how do we do that? One of the ways we do that is with CDs have helped us do that, and it's kind of cool. The CD is, you're familiar with them, you've seen them, and if you look really closely, if you had a microscope, you would notice that there's a little groove in there that has been cut by a laser that is either raised up or lowered down. It's either got a high point, which we call a land, or a low point, which we call a pit. And that's all it is. It's a long track that spirals outward from the middle that has these pits and lands. The idea is that a laser beam shines on this little CD thing, and it reflects off of it back to a sensor. When the laser beam is hitting either a pit or a land, it just bounces back and light gets back to the sensor, and the sensor says, cool, it's on. I'm going to call that 1. But when the laser crosses over the boundary between the high point and the low point, part of the laser beam, let's see if I can draw this here. Okay, so here's my CD up close. Okay, it's got these high points and low points, which are supposed to be the same height. Here's my laser beam coming down. When it hits here, it just bounces back to the receiver. Nothing changes. That's a 1. When it hits here, it bounces back to the receiver. Nothing changes. That's a 1. But when the laser beam is coming right along this edge, some of it hits here and bounces back, and some of it goes down here and bounces back. It has a different distance. And if this distance is just so perfect that when this beam comes back, it's perfectly out of phase with the other part of the beam, it cancels it out, and you get destructive interference, and the laser disappears for an instant. And the sensor doesn't get a laser beam back, and it says, oh, that's a 0. Okay? So 0, 1, 0, 1, 0, 1, 0, 1. Yeah, huh? Okay. Excellent question. So does the distance matter? It totally matters. This distance here has to be 1/4 of the wavelength. Okay. So let's talk about both of those for a second. So does it make sense why this has to be 1/4? Because this total distance down and back has to be 1/2 of a wavelength, so it meets out of phase and destructively interferes with itself. Then the width, what it does is as this thing rotates really fast, the sensor knows that it should be checking every so often. So yes, there is a distance in there. So zeros exactly all together. Exactly. Does everybody understand this idea of how the interference happens on a CD and why this depth has to be 1/4 of the wavelength? Excellent. We'll get there. Okay. Here's kind of a picture. Yeah? See what we're talking about here? Okay. So here's your CD. You look up close, it's going to have actually a layer, a protective layer, like a lacquer coating, and then it's got high points and low points. And at any place where you have a pit or a land, you're getting zeros. But at the interface is where you're going to, they said, I called it a 0. They just did it the opposite. Okay? You're going to have a different signal at the boundary between those two. Okay?
So then do they account also?
All right. So there are other storage devices. DVDs are called, okay, digital versatile discs. Very similar to a CD. The only difference is it has smaller pit lengths. Okay? So the sampling rate is actually much more rapid. And they can do multiple layers, so they can store a lot more information. Now, Blu-ray, think about Blu-ray is kind of the new thing everybody's talking about. Think about that for a second. It's a blue laser instead of a red laser. It has a shorter wavelength. Therefore, the pit depth doesn't have to be as deep. And you can store more information closer together because also the width of that whole track can be a lot narrower. You can make them closer together because you're dealing with small. Gamma ray is going to be the ultimate system. Okay? So those are DVDs. Now, it can, I don't know exactly how they do it, but instead of there just being one layer, there can be multiple layers that the DVD reader can go to. And so you can actually, it's like a, yeah, and I don't know how it does that, but it can do that. So it's like it can be like a stack of DVDs somehow, okay? LP is good old school. That's just vinyl, you guys. Long playing. And basically, LP is not digital. The way those things worked is you had vinyl, you etched a groove in it with a vibrating diaphragm when someone was singing or when it was recording music, and it etched it in there. And then when you replayed it, you had this little needle that would vibrate as it was dragged through the grooves there, and it would create an analog signal, and you'd listen to it. It's really awesome stuff. Much less storage capacity and easily damaged. If you kept your LPs in the sun, you're bummed. You warped your records, and then you couldn't listen to them anymore. It was always a sad day when that happened. Okay. Definitely didn't want to keep your LPs in the car. And you couldn't play them in the car, right, because they'd scratch and stuff. You couldn't dance too hard because you'd scratch them. You know, you got to be careful. 8-tracks were sweet, okay, which we don't even talk about 8-tracks. But we do talk about the next ones, which are 4-tracks, cassettes, okay? Now, a cassette, you guys have seen cassette tapes, right? You guys know what they are? Yeah? Okay. Cassette tapes were awesome when I was your age. I had the sweetest cassette collection you could ever see. Yeah, good. Okay. And it's just, if you ever notice, it's a little piece of tape. It's a magnetic tape, and it stores its information magnetically. And if you think about, basically, it's dragging that tape past an electromagnet where you can vary the voltage, which varies the magnetic field, which changes the way the magnetism is stored in that tape, and then when you play it back, it does it in reverse. You got a changing magnetic field on the tape, which creates a changing voltage in the sensor, and then you get your information that way. Okay. This is kind of cool.
What about laser discs?
Oh, I think laser discs were similar to DVDs, but they were huge, right? They're like.
Yeah, they're awesome. Yeah. I laser discs like that.
Ways of storing? Okay. Here are the other storage devices that we can store. There's other ones too, but floppy disks, man. These were cool. Remember these? Okay. They called them floppy disks. The first ones were 5.5 inches big. They're about this big, and yeah. And it had, if you looked inside, it had a little magnetic, little rotating disc that stored information magnetically. Okay, those 5.5-inch floppies, they stored 360 kilobytes. Okay, and that was huge back then, right? You could like.
Those were better than iPod storage. Instead of having the tape that goes around, you had like a whole.
Yeah, exactly. And you could therefore, you didn't have to rewind or fast forward to get to where you needed to. Exactly. It could scan through it, and so what do they call it? It wasn't sequential. There was another way of getting it. What's that? Punch card. Oh, I remember those. Okay. Then do you guys remember Then came the 3.5-inch floppies that had the hard plastic case. They were about this big, and maybe this is the one you guys remember. You guys may not remember the 5.5. The hard case, right? And those stored 1.44 megs, and those were like super radical, and they were hard, they were protected, but inside it was still a flimsy little magnetic disk that stored information magnetically. The information is stored concentrically, okay, in rings, so it can be accessed directly. That's the word I was looking for. Rather than with like a tape, you always had to fast forward or rewind to get to the place you needed to. So that was sequential storage, which was a little bit more time consuming. And then hard disks came along, and now pretty much every device you have has a hard disk in it. And if you actually took a hard disk apart, you would see that it's like a stack of disks, aluminum disks that are on a spindle that spin, and you have a reader that can go into each layer and look for information that way. Okay. Yeah, I had one of those. The zip drive. There's some pictures. Okay, so hey, look, there's the LP album up there, right? That was pure analog. That little needle, the thing's rotating, the needle's just vibrating with the groove that's been cut in there. Then here we had our cassette tapes. Yeah.
No laser discs.
Yeah, no laser discs. Over here there's our 5.5-inch floppies and our 3.5-inch floppies, and here's a hard drive. See how the hard drive is like a layer of disks? So it's like, and then this little thing's the reader that goes in there, moves.
It goes in and out of the side.
There's a gap between each one, and I suspect that there's a reader on each one too. The whole thing is like an arm that can move in and out and read at all different layers. That whole thing's spinning up and rotating and all stuff, totally. Okay? So why do we even bother doing this? Why do we digitize everything and store it? Well, there's pros and cons, and mostly there's pros, and that's why we do it. The capacity is enormous. All you got to do is store ones and zeros. Easily access to information, easy retrieval, pretty reliable. Data can be copied and erased very easily. Data can be encrypted. It can be processed by a computer. It's easily transported. All those things are great. Disadvantage is if you get one small error in the stream of data, it can be pretty catastrophic. Yeah, like
Microsoft.
on your startup thing, if you miss a couple ones and zeros, boom, everything's off, right? And so that's the main drawback. But again, that doesn't happen very much.
Well, there's also the disadvantage of
There is a diminishing in quality in terms of like music, yes, but in terms of just
photos, videos.
yeah, you're right. You're right.
Well, in colors wise.
But we're getting to the point where that's not necessarily true anymore. Where the ability to store the data, the amount of data storage we have is getting so that it's not so much true anymore. But I hear you, certainly.